We simplify this one, we get here 2r square minus 2r minus 3r. That will be minus r will be minus 3r minus 5 equal to 0. So we take this one, and this is my coefficient of x to the power 4. So I take this equation and factorize this one. As I told you, we need the value of r. R was the number, and we say they will calculate this one. So this equation is known as an indicial equation. This famous now, this non-indicial equation. We are going to this very important part of our discussion. There we find the roots of this equation. We factorize this one, we get two roots here. We write here 2r square minus 5r plus 2r minus 5, taking common r from here and plus 1 from here, and taking 2r minus 5 from here, we get here two value roots. This 2r minus 5 equal to 0 and r plus 1 equal to 0. That give me the value of r is equal to 5 by 2 and r is equal to minus 1. We take this as value r1, and this we can take anyway. You can take the opposite to this one, doesn't make any difference. Now third is that we substitute. We take now, this is the first value, r1 is equal to 5 by 2. This gives me a solution. We are having here now the solution will be y equal to sigma n is from 0 to infinity c0 x to the power n minus 5 plus 5 by 2. This will be my y1, and y2 will be equal to sigma n is from 0 to infinity. Here is cn 0 to infinity. We're having cn x to the power n minus 1. So we will find this one. So we having already this solution. This is my recursion relation. I will substitute the value of r equal to 5 by 2. I get here 2 into n plus 5 by 2 n plus r. Then here n plus 5 by 2 minus 1. Then we are having here the value n minus r minus n plus 5 by 2. And then we are having here minus 5 cn. Then we're having here this equal to minus cn minus 1. I simplify this one. So we are having here the recursion relation. We can just simplify this one, substituting the value of n is equal to 5 by 2 here, r equal to 5 by 2. Simplify, we get here n into 2n plus 7 cn plus cn minus 1. We can write cn is equal to minus cn minus 1 over n into 2n plus 7, where n is bigger than 0. This is my recursion relation. So this I get here as a recursion relation. And with the help of this one, I can find the values. N is bigger than or equal to 0. When I take n equal to 1, put here n equal to 1, we get here n equal to 1, this becomes c0, and n equal to 1, we get here 1. Get to 2 plus 7 is 9. So we get here c0 by 9. Then we take n equal to 2 and put here 2, we get minus c2 minus 1 is c1, 2. Then here 2 into 2 is 4, 4 plus 7 is 11. So we get here 2 into 11, that's c1 over 22. Where the value of c1, that's equal to c0 by 9 with minus sign. This put here the value of c1 is c0 by 9, minus become plus, and 9 multiplied by 22 is 198. Then we take n equal to 3. When we take n equal to 3, is c3 minus c2. N equal to 3, we get 3 into 6 plus 7 is 13. So we get here the c2, 3 into 13, that's equal to 39. Put the value of c2. c2 is my c0 over 198. Simplify, we get minus c0 over 7722. And then we are having our equation y1, that we take n equal to r equal to 5 by 2. And when we take r equal to 5 by 2, we get y1 is n is from 0 to infinity cn x to the power n plus 5 by 2. So here we can write here x to the power n, x to the power 5 by 2, because this is not depending upon n, we take it out. We write here x to the power 5 by 2, sigma n is from 0 to infinity cn x to the power n. When I expand this one, so my y1 is equal to x to the power 5 by 2, c0, here I get c0, x1, c0, x to the power 0 is 1, c1 x, c2 x square, c3 x square, and so on. Now I substitute the value of c1, c2, c3 in terms of c0 in my equation, and then taking here common c0, we can write this equal to c0 x to the power 5 by 2, and inside I got here 1 minus x over 9 plus x square by 198. I get here minus x cube over 7722, and then we have plus, we have minus, and so on. So this is my one of the solution, series solution is my y1, and here this is solution I get here when I take the value of x equal to here r1 is equal to 5 by 2. Now I left with this value r equal to minus 1. We put here in our equation r equal to minus 1, and then we solve it. We take our recursion relation, that is 2n plus r minus 1 minus n plus r minus 5 Cn and plus Cn minus 1 equal to 0, n is bigger than equal to 0. Now I substitute here the value of r equal to minus 1. So this become 2 into n minus 1, and here become n into r minus 1 and n minus 1, and here n minus 2. You get n minus 1 and 5 Cn. We simplify this one, we get here n into 2n minus 7 Cn, and here plus n minus 1 equal to 0. We take to other side, and this is my new recursion relation for the value when I'm taking here n equal to minus 1. Now I substitute the values of n. I take n equal to 1. I get here C1 is equal to minus C0. N equal to 1 is 1. Into n equal to 1, we get here minus 5. So minus 1 becomes plus and 0 over 5. So then is n equal to 2. When I take n equal to 2, I get here C2. N equal to 2, I get here minus C1. N equal to 2, I get here 2 into minus 3. Here 4 minus 7 is minus 3. So minus minus plus, we get here C1 over 6. I put the value here. I get here the value of C0. I get here 1 upon 6 into 5 is 1 upon 30. And I get here C0. Now n equal to 3, when I take, I get here the value of C3. Substitute the value of n equal to 3 in our equation. I get here minus C2 over, I'll get here 3 into 6 minus 7 is minus 1. I get here minus C0 over C2 over 3. I put the value of C2, I get here 1 over 90 into C0 and so on. So we can continue like that one. Now I'm going to substitute, get the value of y2 from here, and my y2 is in summation form is equal to sigma, and is from 0 to infinity. We're having here Cn x to power n minus 1. So I take x minus 1 out, and inside I'll get a sigma, and is from 0 to infinity. I have x Cn x to power n. We can expand this one. We get here x to power minus 1, and we get here C0 plus C1x plus C2x squared plus C3 x cubed, and so on. So when we put the value of C1, C2, C3 in terms of C0, I will get here this my y2. My y2 is equal to C0 x to power minus 1, and then I'm having here C0 plus C1, and C1 is equal to 1 upon 5 C0x. Then we have plus C2. C2 is 1 upon 30 C0 x squared. And then we have this C3. C3 is 1 upon 90 C0 x to power 3. Then plus so on, or plus minus 1, we get this one. I take C0 out. I get here y2 is equal to x to power minus 1. I get C0 out, the constant. I get here 1 over x over 5. Plus x squared over 30, then we have plus x cubed over 90, and plus so on, and this is my y2. So if I want to write my general solution will be y is equal to, I have k1 y1 plus k2 y2. So I multiply this constant, I can just absorb the constant, I don't need to write it again. So I already calculated the value of y1, that was x to power 5 by 2, 1 minus x by 9 plus x squared by 198, and so on. And we have already calculated the value of y2, substitute the value of y1 and y2 here. Because we take the constants multiply the constant, become another constant. So we don't need to write here C0 also in the last one. So here we get the value k 2x to power minus 1, and the value of y2 is 1 plus x by 5 plus x squared by 30 plus x3 by 90, and so on. So this is my general solution of my differential equation. And this we are using Frobenius method, and we have found the solution about the regular singular point. Our regular singular point was x equal to 0, and that's how we can solve it. Because in the power series, we said we find the solution about only the ordinary points, and here we say in some of the very important problems, we need to find the solution even about the point which is a singular point. So then we having irregular singular point and singular point, and we here find the method for finding the solution about the singular point. We have some more example regarding this method. And here in this case, we were having the two values of r1. r1 was 5 by 2, and r2 was equal to minus 1. And we take here r2 minus r1, this minus 1 minus 5 by 2, and we say this is equal to minus 7 by 2 is not an integer, so we can get the solution as y1 and y2. In case this is an integer and they're equal, we have some changes in our solution, in our general solution. Inshallah, we'll discuss next time. Thank you very much.